Great.
Okay.
Welcome everybody to another term's Oxford Discrete Maths and Probability seminars. So we're delighted to get started with Augusto Teixeira, who's going to talk to us about the sharp phase transition for interlacement percolation. Thanks very much, Augusto.
Thank you for the invitation. It's a pleasure. I'm happy or not enjoy the in-person cake, but I will promise to visit soon. Okay, so this talk is based on a joint work with Hugo, Shubhajit, Pierre-François, and Franco. This work that it's based on is a series of 3 papers on, they're very technical, and I will refrain from going to this rabbit hole so much, and I'll try to do a more of a general talk on the subject of sharpness and percolation in general, and only in the very end I'll talk about the interlacement part, the most technical part. So the overview is this. We're going to talk about sharpness in percolation. Then I'll introduce the model just to state the main result. But once we get back to the ideas of the proofs and things like this, I will step back again and talk mainly about the general concepts. So first, percolation in general. It was introduced by Broadbent and Hammersley. It's a very well-known model for a random environment. So the model is very simple. The questions are simple to state, but several complicated and still unanswered ones remain open. So you start with a lattice, an infinite graph. We're gonna fix here the lattice ZD, and for every 2 nearest neighbor sites, we add an edge. And this edge will be declared open with probability P and closed otherwise, independently for every one of them. And we'll be interested in connectivity properties of this thinned random graph. So here's a simulation. And when I say we are interested in connectivity properties, we're going to focus for now on the probability that the origin is connected through an open path all the way to infinity. This is a measurable event. We can define its probability, theta of p. It depends on the parameter p that we started the model with. And we can use very simple arguments to show that theta for p very small is 0, just counting paths. And that for p close to 1, theta is actually positive, or a whole interval, that using a counting surfaces dual argument that we're going to get back to. So that means that there is a phase transition. This function theta cannot be analytic because it's 0 for a whole interval and positive for a whole other interval. If you plot the function, it's going to look somewhat like this. And it's natural to look at this value PC where it transitioned from 0 to positive. We define it implicitly as the supremum of all p's where theta of p is 0. So, of course, there are many, many questions on this problem that remain open. We're not going to talk about them. The most important of them being whether theta is continuous from dimensions 3 to 10. It has been answered for dimensions 2 and 11 and above, with the 11 being a new result improving from the previous 19. So, and also the behavior of theta as it approaches PC is an even more fascinating question in my opinion. But we're not going to focus on those. These are still widely open. We are going to talk about sharpness, which is, in this context, a much better understood property. So first, subcritical sharpness. What does it mean? We defined PC in a very implicit way, just the supremum where the function theta is 0. So there is no chance to connect to infinity, but we could wonder how quantitative is this convergence to 0. We know that below PC, the probability to connect to the boundary of a very large box goes to 0. But this convergence could be taking place very slowly. But remember that path counting argument I mentioned, although it didn't show, it actually shows that the probability to connect to the boundary of a large box decays exponentially in n. But this argument was perturbative, so it only holds for p smaller than 1 over 2d. So if you want to improve on this, we would like to see when this transition exponential decay stops holding. So we could define another implicit critical value that I'm gonna deviate from the standard notation. I'm gonna call it p double star. And it's gonna be clear why I did that soon. So it's the supremum over p's for which this exponential decay holds. So there exists small c and big C such that the probability can be bounded in such a way. These c's may depend on p. So it is usually when this constant p double star is introduced, people go straight to the second theorem in the slide, but I'm gonna be a bit more historically accurate, not much, but a little bit more. And I'm going to mention an intermediate result, which is by Hammersley, showing that p double star is actually equal to p triple star, another value that we're going to introduce, which is the supremum of the p's for which the expectation of the size, I forgot the size there, but the expectation of the size of the cluster of the origin is finite. So, okay, what's the idea of this result? Obtaining an exponential decay is something that is very useful. If you want to understand your random media, your connectivity, knowing that it decays exponentially is as good as it gets. But by being such a strong statement, it's hard to prove. So if you want to show that this regime of exponential decays extends as far as possible, you'd like to have an easier definition. So that's where this p triple star comes. Of course, if the decay is exponential, you can sum over all the connected points and prove that the expected size of the cluster of the origin is finite, but the other direction may be much easier. That was the hope of Hammersley. And indeed, in a series of works, first by Menshikov, all these works independently prove the stated result, but first by Menshikov, using renewal structures, then Aizenman-Barsky using differential inequalities. Then there are more works, a very famous one by Duminil-Copin and Vincent uses a very nice function called theta p of s. It's an amazing way to prove this, but they all prove that PC is equal to P triple star. What does that mean? That all through the subcritical phase you have exponential decay. And by stating this in this very slow form, but first mentioning Hammersley, we're gonna mimic what happens to other models. So in other models, this also happened in this two-step procedure where you first define what you want, which is the fast decay, then you define what may be easier to prove, and then you prove it. And this also happened for the supercritical phase, something that's also not sometimes fast forwarded in percolation courses. So I'm going to define something slightly more complicated. The supercritical phase is slightly more complicated. I'm going to define two properties of a value p. So I'm going to say that prop x of p holds, and x stands for existence. It's kind of the fact that the infinite cluster exists locally. So if for every if the probability that a ball contains a cluster with large diameter, say 1/10 of the diameter of the box, goes to 1 very fast, exponentially fast. So this is the existence property. And then I'll also define the uniqueness property, because this first one alone could give you a very fragmented result with no interconnection between these swarms. So the uniqueness of P holds if the probability that all the clusters, open clusters inside the box that have this large diameter are connected within a slightly larger box, also is a very likely event. With this tool, you can basically do whatever you want. You can show that there is an infinite cluster, for example, by just gluing things in larger and larger boxes. This probability will be summable, and the complement of them will be summable, and you can use Barocatelli. You can basically play Lego with this. You can go anywhere you want. You can, for instance, show properties of the random walk on this cluster or chemical distance within this cluster. But the first problem we identify is that the second requirement, the uniqueness one, is not monotone in P or in the configuration, if you want. Because if we open more edges, it tends to improve the connection between, say, C1 and C2. These clusters have a bigger tendency to be interconnected, but you could be creating a third large cluster that's isolated. So there is an increasing part and a decreasing part, and this will play a big role in the rest. Again, this can be shown to hold for large P's. So remember that the dual to the counting argument is a counting surface argument. It's not how it's usually done in percolation course, but in any dimension, you can show the percolation exists by counting dual surfaces. And if you use that argument, you can show that for P large, not only there is an infinite cluster with that touches the origin with positive probability, but these two properties, XP and unique P, hold. So it's tempting to define this three-phase transitions in principle, right? P double star when exponential decay in spherical phase happens, PC where the infinite cluster appears, and P bar where from then on XP and unique P hold. We already saw that P double star is equal to PC, so the first phase is a unique phase. But what about the second one? It was also proved in two works. So first Chase, and Newman proved that PC, sorry, not PC, I'm sorry for this mistake, it's P bar. the supremum over, I didn't even define it, I'm sorry. Oh no, it's here. The infimum for all P's for which the two properties hold, it's actually equal to another easier to handle critical value, which by the way is monotone. It's very important, called P slab. I'm not going to define it, but basically states that there is percolation in a thick enough slab. You don't need the whole space. You can look at a thick enough slab and
what is P slab? What is slab? What is P slab?
Yeah, so I was trying not to define it, but let's let's do it. So P slab is the following. I say that a value of P percolates in a slab. Suppose, for example, that we are in dimension 3. So I say that P is slab supercritical if there is a K large enough so that I take the plane times an interval of length K. So that's why it's called slab, because there's a slab there for which there is percolation. So for every P, if I find a thick enough slab that I find percolation inside that slab, I say that this P is above the P slab. And P slab is just the infimum. So it's the infimum of values for which a thick enough slab percolates. And it's monotone. It's much easier to treat. And it was proved by Chase, and Newman that it's equal to the P bar that is, very strong exponential decay. By a very nice argument. It's a kind of onion peeling argument. I really like it. So if you try to join these clusters in a box, you just peel the box as an onion, trying to join in every one of the slabs of the skin. And it was later proved in a very celebrated work by Grimmett-Marstrand that P slab is equal to PC. So the supercritical phase is fully well behaved, meaning that XP and unique P hold. Now there is another proof of this result by Contreras and Tassion, which is very nice, and it holds for other graphs as well. Okay, so this was a review of sharpness in Bernoulli percolation. And now we are going to talk about another model, not the independent percolation, the random interlacements, which is very interesting on its own. But if you're not interested in random interlacements per se, you can think of just a much more complicated model that served as a milestone for things that worked on independent percolation, whether they can or cannot be translated to more complicated models. So it was introduced by Sznitman in 2007. What it consists of is basically a random environment, just like percolation. Independent percolation is a random environment obtained by independently opening all the edges of the lattice. Here we're going to obtain a different environment that is not IID. It's very dependent, but it's just, you can think of it as a random subset of ZD as well. It has a peculiarity that it can only be defined for D larger or equal than 3. It's very related to other problems, like the trace left by a random walk on a finite graph, or large deviations, questions about the random walk. There are many questions that you can connect to random interlacements. Questions about the Gaussian free field, for example. But as I said, we're not gonna focus so much on the model, more on the fact that it's a milestone example for very dependent percolation. So here's how to define it. Okay, I'm not gonna refrain from defining it, but I'm gonna define it only on a box. So take a box R, and for every point at the boundary, you sample a random variable with this distribution. Take up the probability to escape from that point to the box. Since we are in dimension 3 or more, the random walk is transient. So there is a chance that from that point to the boundary, you jump outside and you escape. You never visit the box again. That's called ER of X. So you sample a Poisson random variable with this exact intensity. We call it NX. And for every one of these points sampled at the boundary, start a random walk. So the random walk now can enter it. It was sampled according to the escape probability, but now it's not conditioned on escaping. It can enter the box and make this
What is
there.
ER? What is ER of X?
ER of X is the probability that starting at X, you escape the box R. You first jump outside and never visit the box again, the simple random walk. So it gives higher weight to the corners, a little bit higher weight, and the total mass grows like n to the d minus 2. So you see that the number of points you're going to sample is not going to grow as the volume of the box, nor as the surface, but as n to the d minus 2. And this 2 is going to be compensated because the random walk is kind of a two-dimensional object. So you end up with a density of points covered. So the nice thing about this construction is that it's consistent. If you take a box that's slightly larger, the fact that you chose this ER of X makes it so that the bigger construction restricted to the smaller box gives the same law as if you have started with a smaller box to begin with. So that means you can extend it to the whole lattice.
Sorry, so the output is the union of the traces of these walks, is that right? Or something?
Yeah, the IU is given by the trace of all these random walks intersected with R. IU intersected with R is the trace of the random walks intersected with R. So of course, outside the box R, you see that you're cheating because you see the corners of the boxes. But can you see my mouse? Oh yeah. So if you look outside the box, you can see that the beginning of the walk, but from the box perspective, it feels like they were coming from infinity. And that's especially because you chose the escape probability as the intensity measure. And this measure is what you obtain as a limit. For example, if you look at the random walk on a torus or a box, a finite box, and you look locally, because it's going to escape, then it's going to mix for a long time, and it returns, it's going to return with this Poissonized escape probability. Okay, but let us just look at the properties of the model. You can extend the model to the whole lattice, and then it's a very dependent model. For example, the covariance between 2 points, like the probability that X is covered and Y is covered, decays as a polynomial of the distance, which is very bad. For one thing, all these counting arguments fail miserably. For example, oh, I didn't say what U is, I'm sorry. So you can do the same, but instead of taking the escape probability, you multiply it by U. Now you can increase the number of walks, the density, or decrease it. So that's analogous to the P parameter in the independent percolation. So now you can look at IU for each value of U. And so as U increases, more random walks enter the picture, IU becomes more dense. So you expect maybe for large U to percolate. And for small U, less walks enter the picture. So you expect it, okay, not to percolate is hard because it's composed of infinite walks. So for every U, it actually percolates. And not only that, it's a connected tissue. All these walks eventually meet directly or indirectly far away. So I is basically a connected infinite set for no matter how small the intensity. So people started looking at the complement. So the connectivity of I is well understood. So what about the vacant set VU? So this is just what you get when you remove the fabric IU, and you're left with something that decreases its density as you increase it. And you can define a critical value the same way implicitly. The infimum of U for which the probability to connect in the vacant set to infinity is 0, and it does undergo a phase transition. That was proved in 2 works by Sznitman and then Sudaravicius and Sznitman. So indeed, there is a phase transition on this vacant set of random interlacements. There is now a nicer proof by Balashrath. And you could ask yourself questions of sharpness. So is this phase transition well behaved in the sense that we saw for Bernoulli percolation? So
can you write what is U? What is U? Where is U? What is U?
Oh, sorry.
U?
So U is a positive parameter that will play the role of the same role as P in the independent percolation before. So I said that you sample a Poisson number of points in the boundary of the box, but the intensity is the escape probability times U. So now you have a parameter that you can, because I said the nice property about the escape probability is that make it the construction consistent so that you can extend to the whole lattice. But if you multiply by a constant, it's also consistent. So now you use that constant to increase the density of the walks, make like more walks enter the picture as you increase it because you're sampling Poisson variables with higher mean. So more points will appear at the boundary. So as U increases, the interlacement becomes more dense and the vacant set becomes more sparse. So what I'm going to talk now is basically the history of sharpness in this model, because as I said, the usual arguments break because of this very slow decay of covariances and other rigidities in the model. But you know, the same path was followed. Can we first, what do we want from the model? We want to show that there is an exponential decay. This is hopeless. It's shown that it doesn't work, that doesn't hold in all dimensions, but okay, you stretch the exponential decay does hold. So if you define U double star, now this is the motivation for calling the previous one P double star, as the infimum of the densities for which the probability to connect to the boundary of a box decays as a stretched exponential. This indeed is finite. So this, for large values of U, the interlacement set is dense enough, the vacant set is sparse enough that is not only does not contain an infinite cluster, but it has fast decays of correlations. Now you could take the infimum as we took and see if U double star is equal to the critical point. And in this paper by Sidorowicz and Sznitman, they showed that it's equal to a weaker version. So you see, it's just the infimum for which the boundary of a box is usually not connected to the boundary of a bigger box. The probability that a box of radius n connects to the boundary of a box of radius 2n goes to 0. So you see, it's a big step. Instead of now trying to prove this stretch exponential decay, you're just trying to show that the boxes don't connect. In the supercritical phase, you can define XU and unique U the same way as before, but I'm putting a prime here because it's a stretched exponential again. Cannot hope for exponential decays. And it was proved in 2 papers, first dimensions larger equal to 5, then all dimensions, that U bar is also non-trivial. So if for values of U very small, there are very few random walks entering the picture, and the vacant set is dense enough that it satisfies XU and unique U with the prime. But there was no notion of U slab. So an easier version to prove, because U bar is non-monotone. So it's problematic, and it's has all the decays are hard to prove. So there was little hope that U bar could be proved to be equal to UC without first weakening it to something similar to U triple star or U slab. But trying to look at this model on slabs is the model changes too much. So the independent model, when you restrict to a slab, it looks like itself. But this model, when you look at a slab, one slab adjacent to another is not independent at all. So slab is a less of a interesting concept in this context. Okay, so this is the main result that I want to present. If we define, I'm going back to XU and unique U because there was a slight change in the definition, but basically we prove that U double star is equal to the critical value U star, which is equal to U double bar, which is the supremum for which existence and uniqueness hold. So basically we have sharpness for this model. One interesting observation to start with is, if you remember from Bernoulli percolation, for independent percolation, the equality between these 3 phases was proved in 2 works, one for subcritical, one for supercritical. In our case, we prove all of them at the same time, and it's actually a forced thing. We don't know how to prove one side without proving the other. It's going to be clear why, I hope. Second, the uniqueness was changed. Now, instead of looking at a single value U, we look at 2 values, U and V, and we ask the clusters to be vacant in U and to be connected in V. So we want this to hold for all V's smaller than U. And the reason for this is, remember, the XU and unique U is not monotone. So we really have to make sure that it's not monotone, but one side is increasing, the other side is decreasing. So we really have to take one parameter for each, and we cannot take them equally. V has to be even slightly smaller than U is enough, but not equal. So yeah, that's a weakness of the statement, that we need these 2 parameters to be sprinkled, as we say. But I think Pierre Francois and another group is trying to remove this weakness and get the same original definition. And by the way, I wrote it wrong. There is stretched exponential decay, not exponential. And this statement, it looks abstract, but it has several applications. Several of the previous studied applications of random interlacements were stated in terms of these critical values. So, for example, you're studying the random walk on a torus, you just say that you know how to prove this and this for all values smaller than u double star. So does it hold all the way to the critical value? I don't know, because I don't know if u double star is equal to u star, but this is reduced to this very question. So several of the previous statements were conditional. For example, also the large deviations for simple random walks. So now most of them are settled, except the ones that don't allow for a sprinkling. For example, if you take the vacant set in a supercritical phase, it's dense, it has a unique infinite cluster, the infinite cluster has a density, and so on. Does the random walk inside this cluster satisfies CLT? We don't know, because the only conditional work doesn't allow for sprinkling. So yeah. Okay, so this was the interlacement intense part. I want to step back and talk about the new tech in the area that can and is being applied to different models. So if you have another percolation model that's not independent, and you want to try to show that it has a nice sharp phase transition, now there is hope. I will mention three works that have already been published. More are being worked on. So the Gaussian free field, level sets of the Gaussian free field is another very dependent random subset of ZD that has been proved to undergo a sharp phase transition with these techniques. The Voronoi percolation has been recently tackled with this for any dimension. Here we have Olivier Jordan, who worked on the two-dimensional case. Now, at least sharpness is understood in the high-dimensional case, not the continuity, but sharpness. And also some other Gaussian fields that are not free. So how do we go about this proof? So the ideas are these bullet points. First, we are not going to prove anything from scratch. We're going to assume the sharpness of Bernoulli independent percolation and construct from it. So this is a big difference between what I was trying before, and I gave up this problem in my PhD postdoc because I thought, okay, it is impossible to adapt any of the existing proofs to this dependent context. But the idea is exactly the opposite. Let's assume that all we know is that independent processes undergo a nice phase transition, sharp, and we just carry from there slowly all the way to the dependent one. The second step is already present before. We have to weaken this notion of X-pen unique to something more manageable. Then the first step is to go from independent to finite range dependent models. That can be done in a very nice degree of generality. It's amazing. And then we go from finite to larger finite, increasing the radius of dependence until we interpolate all the way to the infinitely dependent model. So this is the plan. So the first thing, as I said, is to weaken the critical value. When you want something that is monotone. So we just define this M of R, which is something growing very fast with R. Super polynomially, but not stretched exponential. That would be too much. And we say that we are percolating. Sorry, we are not. Okay, I don't want to state it like this. Let's just take some value of u, and you want to know if a box is connected to a much, much bigger boundary far away from it. And the probability should be small, but not only going to zero, but going to zero with the basically the radius of the big box to the d. So if you are not in this regime, it means that you oh sorry it's supposed to be non-connected here. That's what's confusing me. So it means that you're very no, sorry, it's correct. It's correct. So in this regime, if you are above this this u, it means that you can find surfaces that restrain the small box, even if you need to look far away. And if you're not in this regime, it means that you can find very easily paths going far away. They are not unique because we don't want to add break monotonicity, but we can find very long paths starting from adjacent boxes. And the probability is so good that we can take a sublattice of these boxes and find these worms all over. We have no guarantee that one connects to the other, but we are very close to having a robust cluster because these worms are very long and start almost adjacently to each other. Okay, so the first result is to show that this is equal to the U triple star. So trying to summarize the idea again. Suppose that we have a certain U that is so good that from a box we find the path to a very far away box with very large probability. Large enough that we can sum this over a sublattice of boxes. So imagine several boxes like this, all of them are connected very far away. These dendrites are not required to interconnect with each other, but by changing slightly the value of u, sprinkling a bit the density, we manage to get them to connect. So this is very inspired by work by Beniamini and Tassion. So I will state the question they posed so that you can see the similarity. So the question they have is not related to the standard percolation setup. You just take a graph, subgraph of ZD, that every point belongs to an infinite cluster. So it could be, for example, vertical lines that are not, let's not imagine that the whole thing is connected because it would make the statement silly. Imagine vertical lines, for example. So they are infinite clusters by themselves, but they don't interconnect to adjacent ones. We chose this graph. Or we could take slabs, or we could take infinite spanning forests. So every point belongs to an infinite tree, but the forest may be composed of non-connected trees. What they prove is that for no matter how small a sprinkling you give of Bernoulli independent percolation, the whole thing becomes connected, almost surely. So you see the connection. We have these dendrites, and for every sprinkling, they join together and become much closer to the U double bar that we wanted. So this can be done in a quite robust way. It's their idea of proof is robust with respect to dependencies. So that's why this is the first step. So then there is a second statement only about dependent percolation, a finitely dependent percolation. And if you forget everything else about the idea of the proof, this is, but you have slot for one idea, this is the one I wanted everyone to keep, because it's such a general statement. Every percolation that satisfies A to E is sharp. What is A to E? So this measure random measure should have respect the symmetries of the lattice. It should satisfy the FKG inequality. So two events that are increasing should be positively correlated. They should satisfy the finite energy property. So if you want to make a local change, you can pay a finite price for it. This measure should be a finite tariff factor of IID. I'm not going to define this, but it's a classical stronger version of ergodicity. And the last one, which is before D, you can construct counterexamples. For example, you could have something that basically flattens out, and as you change your parameter U, it doesn't change the measure. So you're definitely not going to have sharpness if you have plateaus. But this is forcing sharpness, forcing change. So the measure under the parameter U is dominated by a sprinkled measure once you take a union with an independent Bernoulli. So you can compare changes to your parameter with changes given by an independent Bernoulli sprinkling. So with those 5 things satisfied, you have the existence of a phase transition and the sharpness of this phase transition. It's very useful. I've seen, several. Myself, I have proved this for specific models using renormalization and suffering, and I've seen several people doing this, and now I think it's this black box is much more useful. Okay, so for interlacements, we can define a truncated version. So now the task, you have this infinite dependent model, and you have a statement that holds, and it's very general for finite dependent measures. So you can try to imagine a truncated version of your model. In the case of interlacements, we're going to define this IUL, which just take a Poisson point process in the whole space with intensity that decreases with L. And from each of these points, so it's U over L, right? From each of these points, you run a simple random walk with length L. So L as increases, the density goes to 0, but the length goes to infinity. Things compensate, and it was proved that this model converges to random interlacements. So this is our candidate. This is a model that is finite range dependence. It satisfies everything from A to E. So it's a model that's sharp. But okay, it's a very strong cheating, right? This model is finite range dependence. How can we translate the sharpness of it to the sharpness of the infinite random interlacements? So that's the last technique I wanted to talk about, which is called the interpolation. Okay, so interpolation is exactly this. We are going to try to connect the finite one to the infinite one, and we do this first in dyadic scales. So we have to build a coupling that in and on itself took a whole paper from the series. So we want to take the interlacements, like the worms of length L, give it a slight sprinkling, and cover it with swarms of length 2L. It sounds trivial because the other worms are longer, but they are less dense, right? They have twice the length, but half the density. But you can do this. You just have to take the worm with length 2L and, okay, I'm oversimplifying. Imagine it's 2L plus something, just that you can slice the middle part of it and use it for mixing. So if you take worms of length 2L and erase the middle part, 2L, take 3L and remove the middle third, you get, you erase the dependence between adjacent ones, and it looks like a soup of L length walls. So you can do this domination, that's the easy part, but you can also do the other side. So take worms of length 2L, and we can almost cover them with worms of length L with twice the density. I say almost because we didn't manage to get the full coverage. So we cover it in a set that has these boxes removed. So we're gonna set up some boxes very far away from each other. We call it the changing room. So the worms of length L go about their life. When they arrive to a changing room, if there is another one in the changing room, we just say, okay, we don't know what happened there. Are they the same worm or not? And we managed to glue them without, if you don't see inside the changing rooms, you don't know if it's an L or 2L measure. So that was enough for our purpose to work with the measure with changing rooms. Okay, so this was a bit of a pain in our case, but it can be done for other measures in a quite straightforward way. Trying to show that the L1 is dominated by the 2L1 and the 2L1 is dominated on its turn by the L1 with sprinkling all over. So for example, this for Voronoi, this is an easier statement, much easier statement to prove. So this is the coupling. It tells you that basically you can swap the measures by paying very little and sprinkling a little bit. But this is not enough. You have to, in the end, so this is the last slide, I guess. Yeah. So in the end, you have to go from infinite to L. So you see, I'm only showing the lower bound here, but everything can be proved with the inequalities and the sprinklings inverted. And this is enough to show sharpness. Remember that the sharpness has been characterized by now U double star and U tilde. So these two values are only concerned connection between boxes. So if you prove that connections within boxes from one model can be compared to the other model, we are in good shape. So you see, what we need is to show that these boxes have the connection probabilities viewed from the infinite VU or from the finite VUL, they behave more or less the same. So there is this upper bound, sorry, this lower bound. It has a very nice decay, and not only the decay is nice, but it's independent of r, little r. And that's crucial. We cannot make the connection between the thresholds if we have something that depends on r or L, especially L. So it has to be something that only depends on big R. So, okay, we want to connect the infinite model with the finite model. How do we do this? We connect the 2L model with the L model. And we accumulate the error, but it's summable, and it's going to give something just of order R. It's not a problem. Now, how do we connect the 2L model with the L model? We pave the lattice with boxes of length R, and we do the surgery box by box. So we take a box that had worms of length L, and we replace it with worms of length 2L. Now take the adjacent box, do this. Take the adjacent box, do this. And this, you see in the picture, you have some shaded area where you already replaced L worms by 2L worms. And there is one red box where you're going to do the change. Can you show that doing the change only improves your connection? And what's happening inside the box? You are removing the L trajectories, adding the 2L trajectories, and doing some sprinkling only in that box. Does that only help you or not? And it becomes a question of pivotality. Can you change one pivotal L worm with one pivotal 2L worm and back by paying some small prices? You know, this is the basic question. So in the end, the proof is very much inspired by Aizenman-Grimmett's work on the essential enhancements. Although, okay, the details are completely different, but you really are asking yourself, can you replace one type of pivotality by another type of pivotality? If you can do it in a uniform enough way, you're done. Okay, sorry, I know this last part is extremely technical, but I wanted to, I raised a lot of the technicality. I wanted to give some of the in-depth view of the proof, because I know there are experts also in the audience. So thank you very much.
Thank you very much, Augusto, for, I mean, a beautifully judged talk. I really enjoyed that. It's clearly a very technical series of works, and I think you've given us a beautiful flavour of what happens in them. Can I invite any questions from the audience?
So I guess the question is, where does the reusing the sharpness of Bernoulli percolation? Is that inside the big theorem that under A to E?
Exactly. So
Okay.
it's you go from completely independent using your SSS, you prove sharpness for the A to E models. That's where you use the previous results.
And that also involves looking at sort of locally dependent, like the variations of sort of one independent models or something. Is that right?
Sorry?
That also involves sort of locally dependent models, like there's one independent models on, or k independent models on Z, where you have independence at distance larger than k. Is that right?
Yeah.
Mhm.
Yeah.
Anybody else? Did I understand from your slides, you mentioned various other papers that these finite tree interlacement models had been previously studied?
Yes. So when I first saw the definition, I thought, okay, this is, so you have this finite range models. I didn't mention, but I didn't say, but I wrote in the slides, it was studied in a series of works, and actually interlacements are like this. You do your PhD on them, and then you say, okay, now what is not answered is impossible, and everything else is trivial, and that's it. And then people come up with very interesting questions all the time, and keeps coming. So this is one example. Several interesting questions have been raised about the finitary random interlacements.
And what of those remain open?
So one of them is very nice. Okay, it's already not finitary anymore, but it's fixed. It's a random range. So as soon as you take the L to be random, you start to have phase. For the finitary random interlacements, you have a phase transition for the interlacement set as well, right? You no longer have the guarantee to be connected to infinity by an infinite path. You have to join the worms. So there is a phase transition on IU that is going to zero, right? The critical threshold goes to zero. But how does it go to zero? That has been looked at, and I don't think it's been exhausted. But also how the random L's behave. This is the last work I mentioned there by Rath and Rokob, and it guards many questions. You can look at the paper. It's very interesting. Like models that don't undergo a phase transition were initially thought to be boring because there's no phase transition, but they are as boring as bootstrap percolation. As soon as you accept the fact that they don't undergo phase transition and start to try to understand their depth, they sometimes are richer than the ones that undergo a phase transition.
Are there any remaining questions from the audience? I think that's a no, in which case what I'm going to do is I'm going to stop recording, and I'm going to invite everybody to unmute and to give Augusto a big round of applause for a beautiful talk.